Hallmark Hotline, what is your emergency?
And our big snowstorm will surprise them all. At least, I'm guessing we'll have a big snowstorm in the next year.
You know, Nathan, that is a distinct possibility in this area. And yeah, sometimes the trees and plants get caught off guard. Anyway, let's spring forward and get this show moving.
Sam, Nathan, and I are here to help you with math, science, and English, new edition. We are here every Tuesday and Wednesday from 4:30 to 5:30 p.m. You can call us at the number on the screen. It's right, it's normally right up there, but it's not right now. There it is. The number on the screen, it's 720-424-1666. And call us, ask us, and heck, see if you can stump us.
Yeah, and there are so many different ways that you can watch us live. For live broadcasts, you can tune in to Comcast Channel 22 or 882. I think is one of those our HD channel now?
Yeah, 882 I think is the HD.
Okay. There's also Prism TV, channel 8007, or go to livestream.com, click on Discover, and put in DPS TV in the search box. We also take advantage of Facebook Live, so you can find us there at EG Homework. Or if you'd like to see some of our past shows, check us out on YouTube by searching for Denver DPS TV.
Well, that is a mouthful, but as you can see, we really want to help you find us so that we can help you. This show is sponsored by our two high schools. I teach at the Contemporary Learning Academy, and Becca and Nathan teach over at Emily Griffith High School.
Yeah, and in about half an hour, we'll have our weekly science demo, and I heard it will be rockin'.
Oh, yes.
So we'll also take your social media questions from our social media master. Derek, why don't you tell us a little bit about yourself?
Definitely. I'm Derek. Like Becca said, I take the questions and get them over to the teachers, but I'm also the trivia master. At the beginning of the show, I'll give you a trivia question, and then by the end of the show, I want to hear an answer from you. And if you have the correct answer, you will get a prize. The question can be on any subject. Today we have a seasonal history question. In the 14th century, before spring was part of its name, what was the season called?
Interesting.
All right, well, if you think you know the answer to that question, give us a call before the end of the show, and you can win a prize. I think we're giving away, it's 2 tickets to a symphony of your choice. I'd also like to give you our other contact information so that you can send your questions to Derek, our social media master. So you can send those to us at Facebook or Twitter at EG Homework. You could text Derek your questions at 970-680-3771, or you could email us at homework@emilygriffith.edu. So all different ways of getting in touch with us today. All right, let's go to Derek and start answering your questions.
All right. So the first question we have is, I believe, a math question. It says 3 partners, Alex, Bob, and Kathy, invest $36,000, $45,000, and $54,000, respectively, in a business. They share in the profits in proportions to their investment. Last year's profit was $37,500. What is Kathy's share?
Okay, hang on. I'm gonna try it. I need to open the email and I need to just copy that onto. No, this is not gonna work. Quick. All right, I'm gonna copy it from you. Sorry. So let's see. So Alex was 36,000. Bob was 45,000.
Mm-hmm.
And Kathy, was 54,000. Okay. And then
So
they share in the profits in proportion to their investment. Last year's profit was 37,000. Okay. 37,500.
Yep.
Okay. Okay. All right. So what we really need to find out first, who are we doing? We're doing Kathy's. We
Yes,
want to know
Kathy.
Kathy's. Okay. What we really need to find out first is what proportion each person invested into all of this, because that's the portion of the profit that they're going to end up getting. So one thing when we're doing the portion of what we're doing is we've got to find the total amount. That's always going to be the bottom part of the proportion. So we're going to find the total first. So we have 36,000 plus 45,000 plus 54,000, and let's see, 4, 5, 6. So let's do this. So 135,000 is the total. Sorry, let me explain this real quick. All right. So if our total is 135,000, we'll find the portion, we can find the portion that each one of them did, but really we're trying to focus on Kathy, because we want to know how much of the profit that Kathy is going to get. So Kathy, let's do this. Kathy is doing 54,000. She invested $54,000 out of 135,000. So that's going to be my total, or her portion. And if we simplify that fraction, which I'm going to use my calculator to do that, you end up getting, it would simplify to 0.4, or you could also think of this as 4/10. And the way that I did that is I just divided the numerator divided by the denominator, that's it. Or you could also say 4/10. So she's getting, or also, I should also say in percentage form, she's 40%. So that's how much she invested in comparison to Bob and Alex. She did 40% of the investments. So we know that she's going to get the same portion of her profit that she invested. So that means that she's going to get 40% of the profit, which the profit, back up here, was told to us in that word problem, and it's 37,500. So we're essentially trying to find what 40% of 37,500. Now, I could get into a bit about percents and how percent means. So what this really means is 40 out of every 100. So every 100 that's in this 37,500, she's going to be receiving 40 of that. But the way that procedurally you would find a percent of something is we would turn it to a decimal first, and we actually already had that decimal here, 0.4, and then we're going to multiply it by our total. So we're going to do 0.4 times 37,500, and we get 15,000. So Kathy is going to get 15,000 of the 37,500 in profit. We could also find the portion for Bob and Alex, but since this problem it just asked about Kathy, we'll just stop there. So hopefully that helps. Hopefully that answered the question.
Yeah, do you have any, because you can call it proportion 0.4, or you can call it 4/10, or you can call it 40%. Mm-hmm. Do you have any advice on when a student might want to choose which one, or is it just whatever's most intuitive to the student, I think?
Probably whatever's most intuitive,
Yeah.
just because some people are really afraid of fractions.
Mm-hmm.
Some people actually, I had students tell me the other day, they hate decimals, they would prefer fractions.
Interesting.
I know.
I've literally never heard that.
I know, I was really surprised, but it happens.
Yeah.
So I'd say whatever you're most comfortable with. Typically, percents are easiest to understand,
Mm-hmm.
but not necessarily easiest to work with. We always turn them to decimals to work with them, right?
Yeah, and you always have to remember that's out of 100, and
Right.
there's just a little bit more with that.
Yeah.
I usually say if you're going to be adding, then decimals are easier. If you're going to be multiplying like a percent, then the fraction's a lot easier to multiply.
Yeah.
But again, I think it comes down to whatever you feel most comfortable with. Like
And
you
it
said.
also depends on the numbers too. So let's
Right.
say you have 1/3. That's not a nice decimal. That's 0.3 repeating.
Right.
So a fraction would be much nicer to work with in that case. So I think it really it depends on a lot, unfortunately.
Right.
It's nice to know how to do all three and move back and forth between all three just in case the scenario calls for something. One of them works better.
Yeah, I agree.
So, all right, let's go back to Derek and get some more of your questions answered.
All right, so we got a science question. It says, Denver, Colorado is at a higher altitude than Los Angeles, California. Which of these statements is correct? Water boils at a lower temperature in Denver than Los Angeles. Water boils at a higher temperature in Denver than Los Angeles. Or water boils at the same temperature in Denver than in Los Angeles.
All right. Yeah, it's a great question. Super relevant since we live in Denver. Answering a question like this, right, is fairly straightforward. If we just want to know the answer, does it boil? I mean, if you just wanted to cook something, you could easily find something on the internet that would tell you. If we could jump to my screen, I'll just show you a really simple graph. So you might find a graph like this if you ask Google about boiling point compared to altitude. And you can see in this graph that we've got the temperature of the water in degrees Fahrenheit on the left, and then we have the altitude on the y-axis, I should say, and we have the altitude on the x-axis. And so you can see as altitude increases, and this has got us going from 0 feet altitude to 10,000 feet, the boiling point of our water decreases. So we typically hear that water has a boiling point of 100 degrees Celsius, which is 212 degrees roughly Fahrenheit. But you can see that here in Denver, Colorado, where we're at about 50 to 80 feet above sea level, I'm going to find that area just above 5,000 feet right here and come up to this line here on the graph, and it looks like you can boil water here in Denver at around 202, 203 degrees, so almost 10 degrees cooler than in Los Angeles. So again, it's fairly easy to just answer that question using the internet or just get that direct answer, but more important would be to understand why this is the case. So boiling has to do with what's called vapor pressure. So we think about the conversion between a liquid and a gas. We call that a phase change, and we can think of any kind of liquid has what's referred to as vapor pressure, and that's the pressure that the liquid exerts on the air around it to essentially allow its molecules to make a phase change from the liquid state to the gas state. Let me show a picture kind of that idea. This is really small. Let me blow it up here. So hopefully you can see. It might be a little bit unclear on your video screen. But you can see what's pictured here is a jar full of water, and you can see the water molecules down here are just one solid mass, but then we have water molecules floating up above here. And the idea goes that, that there's a natural pressure that this phase change is exerting from liquid to gas, that these water molecules are exerting on the air around it. If the air around it has really high pressure, you can see up here we have air pressure pushing back on the water. If the air pressure around the water that we're talking about is really high, that's going to prevent water molecules from moving from the liquid state to the gas state, from making that phase change. There's another image I can show here which might show this fairly simply. So in a liquid state, we can imagine molecules much more closely bunched together, and then in a gas state, they're spreading out from each other. And the energy that these molecules have, even in a liquid state, molecules are vibrating and shaking, and they have energy inside of them, and we perceive that energy as temperature. And even cool water that we might perceive as cold, even that is exerting some vapor pressure, and some of the molecules there are making that change from liquid state to gas state. And I should actually throw in too that there are some molecules, and you can see here that some molecules are going from gas state to liquid state. So there's this natural exchange back and forth. If the water's cooler, more of it is going to be inclined to stay in liquid state, and if it's warmer, more of it's going to be inclined to change over to gas state. But then what we really want to think about is, so how does this relate to altitude? So I'll just show one more graphic to kind of get this idea across. But the idea goes that when we're at sea level, which is as low as you can be on land, right, without being underwater, you have the most air above you. The atmosphere extends out from the surface of the Earth, and the lower elevation or lower altitude that you are, the more air you have above you, and the more tightly packed that air is. As you go further up in altitude, the air molecules get spread out more. This is why it's hard to breathe in really high places, people who are used to sea level levels of oxygen. When they get up to places like Denver or even higher elevations, they can have a hard time breathing. People who summit Mount Everest, which is over 20,000 feet tall, some of them actually need to bring oxygen tanks with them because the air molecules, the oxygen molecules in particular, are so scarce at such an altitude that folks aren't able to breathe. Looking at this diagram, though, we can see that, again, down at sea level, there's a lot more air pressure, and that's because there's more air molecules weighing down. In fact, if you're down at sea level, you've got more air literally weighing on your body, although given that air is so light, we don't notice really any perceivable difference. But imagine a glass of water, or let's say a pot of water on the stove. If I'm down in Los Angeles and I've got a pot filled with water, as I turn on the heat, what I'm trying to do is increase the energy of the water molecules inside that pot. And when I increase that energy, the vapor pressure of the water will rise and will work to overcome the air pressure that's pushing back against, and I'll show that image again, that's pushing back against the water. Down at sea level, there's more air pushing down on the water, and so the air pressure is higher. So you have to bring the water to a higher temperature to increase the vapor pressure more so that it can overcome that atmospheric pressure and we can get to a boiling state where liquid particles are easily making the phase change to gas. Up here in Denver, we have less air overall, we have lower air pressure, and so that pot of water on our stoves at home has less air pressure pushing down on the surface of the water, so it takes less overall energy that we have to put in to get those molecules to get to a point where they've got a vapor pressure that can exceed atmospheric pressure. So again, just kind of thinking about the reason behind these answers. You know, a lot of the times the science questions that I get are questions that can be answered really quickly, like in a single sentence or maybe even just a single word. But the goal should always be understanding the science behind them, what's really going on at a molecular level or at a cellular level, as opposed to just trying to get the right answer.
I really liked that explanation. It made me understand it.
Thanks.
Yeah.
I always, sometimes I do this thing where I'll start explaining and I'll get into like talking about vapor pressure or something like that, and I'll think, oh my God, there's so much I can say about
Always.
this.
I mean, but that's the nature of science. It's all connected in some way, right? But
Definitely. And maybe I'll just also throw in there that understanding little things like this can allow us to understand other bigger things, right? So actually the very concepts that I talked about here are really, really directly related to some of the concepts we're going to see in the science experiment later. Even though the science experiment has nothing to do with boiling water or even air. But the concepts are still relevant. So, you know, understanding core concepts like how molecules function and how temperature is really just molecule energy, those kinds of things can be really helpful in lots of different arenas.
Yeah,
Gotcha.
it's interesting.
all right. Okay, so let's go back to Derek and get another question answered.
All right, so we got another math question here. It says, how many lines of symmetry does this shape have? And it's a big capital Y.
All right, I can take that one. Did that have, it'd be helpful if I could just pull that up, but I don't know if that's, do you know when that was sent?
Yeah.
It's okay, I can redraw it if I need to, but.
So, should be subject help.
Okay. That's why I wasn't finding it, because this is an image
Yeah.
with the text in there. All right, so we want to know how many lines of symmetry. So I'm just pulling this up. But first, let's talk about, as I'm pulling this up, what symmetry means. Symmetry just means if you drew a line that, in a sense, you could imagine it like being folded over onto itself over that line and kind of looking exactly the same. So one of the things I kind of found interesting about symmetry, and I always tell my students, is have you ever heard about, like, there are studies showing like why people find other people attractive? Have you heard this?
I have heard this, that the more symmetrical a person's face is,
the more attractive
the more
they're considered.
attractive they are. Right.
So Denzel Washington is considered to have one of the most symmetrical faces in Hollywood.
So is Halle Berry.
Halle Berry too? Because if you literally drew a line like straight down their face and like had a mirror and copied this side of the face onto this, they would look exactly the same.
You know those Apple, on the Macs, the photo studio or photo booth? Yeah, photo booth,
yeah.
that's what it's called. So they have one of those things where it cuts you down and it like reflects you,
yeah.
and so then you can put half of your face together with your other half. And most people just don't even look like themselves when they do it.
I should do that because my nose was broken, so it's a little like crooked right here, and I kind of wonder if it would look like a weird.
It might.
Maybe I'll try that. So anyway, that's a kind of an interesting thing about symmetry and how we kind of use it and we don't really think about it, but subconsciously.
Pleasing to the eye.
It is. That's a good way to say it. Very pleasing to the eye. So when we look at this letter Y here, think about, and I'm going to give you a different object. When we talk about lines of symmetry, think about if I did a line like this and a line like this, and these are considered the lines we're going to think about for symmetry. If inside of here I did, say I did a rectangle, you could imagine that if I thought about this line, imagine if you were to, like we just talked about, cut this side out and fold it, and replace the other side. Imagine like I took a mirror and flipped it over that line and replaced the other side. Would it look exactly the same or not? And in this case, it would, right? It would say, if I mirrored this over and copied it, it would look exactly like this side. And the same would go for if I looked at this right here. Let me do this line right here and wanted to think about if this is a line of symmetry. Again, think about if I were to, another way to think about this, if I were to take a mirror and place a mirror right where that blue line is, and kind of mirror that one side over to the other, would it look the same?
Yeah.
And in this case, it would too. And these are not the only lines of symmetry we can look at. We can also talk about diagonal lines, something like this. So I actually have another line of symmetry here where if I were to...
Is it a square?
Let's call it a square.
Let's call it a
Just
square.
to be-
If it's a
that's a
square,
good
then
point.
that's symmetrical. That's not
yeah.
perfect square then.
Let's call that a square. And actually, I'm glad that Becca said that because in geometry, it's really important. I can argue that none of these are symmetrical or none of these lines of symmetry work if I can't be 100% sure
Prove.
that the measurements are the same.
But that's a common one that people like to say. I remember teaching this in middle school. If you have a rectangle and they want to cut it right there,
Right.
and they want to say that's a line of symmetry because it's the same
Yeah.
size piece, but it's not because if you folded it, think of if you
It
took a
looks
piece of
very
paper.
Yeah.
Like
It
if
looks
you took
very
a piece
close.
of rectangle and you were to fold it in half, like fold it at that line of symmetry,
Right.
I'll even just show you what it looks like. It's obviously not symmetrical. You can see they
It's a really
don't.
good example.
Little mountain
Yeah,
range.
but it looks, it makes it look, when you have a rectangle and you draw it, down the diagonal, it really makes it look like they're symmetrical because the pieces look equal. They look
Yeah.
the same, right?
And I'm going to kind of steal Becca's idea here and use that same idea. Like we say this rectangle has a line of symmetry here because if I fold it right there, it's exactly the same on both sides. Or like we said, if I fold it this way, same, right? So that's another really good, I think, visual way to think about it. It might be hard to imagine.
Like
a mirror.
folding over.
Yeah. So when we look at this letter Y, we're asking how many lines of symmetry do we have? In this case, if this were a square, I would have another line of symmetry right here. And I think that would be it, right? 1, 2, 3, 4 lines of symmetry. But with this other shape, let me rewrite square, I'm only seeing one line of symmetry. Right? That line of symmetry would be if I were to go straight down here. And Becca, if you see something else that I'm missing here, let me know. Because sometimes it can be a little, that's not a very good line. Sometimes it can be a little tricky to see these, especially, I can't move it. Maybe I'll move the other figure instead. Especially with figures that, well,
They just don't want to line up.
I know, you get the idea. Especially with kind of odd shapes or like I wouldn't even say odd shapes, but like the
Just
square
irregular,
rectangle,
yeah.
right? Where it's really easy to think that you see a line of symmetry, but it doesn't actually exist. When we look at this value y, or this figure y, the only line of symmetry we have is straight up and down. So that line could be called x equals something if you're on a coordinate plane. But you really have to kind of try to visualize and imagine this. If I were to draw a line horizontally like this, that clearly looks different on top and bottom. If I reflect it over, it's going
Right.
to look a lot different. And you can kind of visualize, or you can draw lines and play around, like that's not going to work.
Yeah.
Nothing here is going to work. So a lot of different ways to play around with this.
There are actually little mirrors that you can. I had them when I taught
did
middle
you?
school. Yeah, little mirrors that you can use to test it. That you lay down on the paper, and then it will reflect what's on one side onto the
Yeah.
other, and so you can see, whether or not it is symmetrical because it actually shows that reflection.
You're going to have to help me find that, actually. I think that'd be really helpful for my geometry class when we talk about this.
Right. Okay. You got it.
We can also talk about, really quick, something called rotational symmetry.
Oh, and that's a tricky one.
Yeah,
that is
that's
really tricky to see.
Very hard to see. What's a good figure to try? I can do a triangle.
A triangle's a good one. I was thinking of like a star.
A star? Yeah, I think I like that. I can't really draw a star very well here. I'll just do it like this.
That one's tough to teach too,
It really is because
it's easy to get the folding thing
right.
sometimes.
And it's sometimes, you know what? I'm not going to do a star. I'll just talk about this triangle really quick.
Okay.
If we assume that this is an equilateral triangle,
Mm-hmm.
since you reminded me, we got to be really clear. Basically what this is saying, like Becca said, it's hard to see this, but can I rotate on here? If I were to spin this around, I don't think there's a rotate option. If this were an equilateral triangle, I could turn it, and I could bring this point right here kind of up to the top. I don't know if that's confusing.
Yeah.
But you can imagine if I were to just rotate it, say 60 degrees, then it would look exactly the same. And if I rotated another 60 degrees, it would look exactly the same. Again,
Right.
like Becca said, it's a little tricky to see, and you kind of have to play around, get used to it a little bit.
Yeah, but essentially if you flip it or rotate it, flip is the wrong word.
Right.
Rotating it is the same thing.
Right.
So.
Yep.
All right, little lesson on symmetry. All right, so we're going to take a little break. When we come back, we're going to have our science experiment.
So sorry, welcome to the Homework Hotline studio, science studio, I mean. So I was just cutting a piece of paper that I'm going to need in just a second here. But we're going to be looking at density today. If you watched the show, you may remember that recently we did an experiment looking at plate tectonics and the way that continental plates or tectonic plates run into each other and how they might subduct. Do you remember this?
Yes.
Right.
It was with peanut butter and
We
graham
used
crackers.
peanut butter and graham
It was
crackers.
good.
I'm not sure the date of the episode. It was a month or so ago.
It
You
was
should check out.
delicious.
It was
It was a
delicious.
delicious
It was a really
experiment.
great experiment.
This one's going to be a little less tasty, but hopefully just as interesting. So one of the things that was brought up in there was this idea that sometimes what you have is when you have two plates hitting each other, sometimes what you have is one that will sink below the other. And the rule that I gave you guys, I don't know if you remember, but I talked about continental crust and oceanic crust. Do you remember which one subducts below the other one always?
thought if
Oceanic
it's-
crust is denser, right?
Yes, oceanic crust is denser.
And so it goes below.
And so it goes below it, what we call subducts, it goes below. So like if this is oceanic crust and this is continental crust, and they hit each other, the oceanic crust should sink below. And Becca just gave it away, it's density that is the difference there. So what is, no, you're totally, no, I don't mean, not in a negative way, in a good way. What is density?
It's kind of like how much stuff you can pack into a certain size, right? So like
Yeah.
if I don't know, I think about like rocks, like
Yeah.
based on the size and how much it weighs, you're kind of packing more into that space.
more
in a
material
sense.
into this space. It's like
Right.
it's like the number, it's like the amount of mass in a given volume.
I always think of like when I pick up a package at home, I get home and then,
Yeah.
okay, there's a package at the door and it's really big,
Right.
you know, and you pick it up and it's really light actually because
Yeah.
it's filled with
Yeah.
styrofoam or
Yeah, the stuff inside is
a very
spread out.
small one that you pick up and you're like, whoa, really dense.
Definitely.
Or like a prop for a movie, right? That like looks like a brick, and you chuck it at somebody, and it hits them in the head, but it's made of foam.
You know, actually, I
So-
have a foam brick and an actual brick that I use sometimes with my students to talk about this very idea. Or even if you saw earlier when I was showing the diagrams related to boiling point, if you noticed, the air is denser down at sea level. It's tighter, it's more packed together, the air molecules are, and it's less dense up at altitude. So we're going to be looking at this idea of density with water and sort of thinking about this idea of can we see examples of more dense things sinking, right? If oceanic crust subducts below continental crust, where's some evidence for that? So we'll look at 3 densities of water. So I've got here ice water, room temperature water, and then hot water. It's not quite boiling. I just checked the temperature. It's about 170 degrees. So still really hot. And actually, we're gonna have to be just a little careful because of that. Okay, and then I also have in my handy dandy pocket here some food coloring items. I was maybe missing one, but that's okay. All right. So what we'll start with is room temperature water. So what we want to do is just kind of see what happens when we mix when we mix things that are the same density. And we could imagine thinking about rocks. No, that's fine, Becca, I appreciate it. So we could imagine on the Earth 2 continental crusts hitting each other and not really subducting above or below each other, or 2 pieces of oceanic crust hitting each other and maybe being the same density. So we'll do that with room temperature water, okay? So, Becca, would you do me a favor and fill, and we'll do this actually in the Pyrex pan. Will you fill that guy up to the brim with room temperature water?
Sure.
All the way up there. And in fact, fill it up so much, Becca, that it pours over just a little bit.
So we're gonna move some of this.
Oh yeah, definitely, please. Let's
So that it pours
see
over?
let's get a clear shot there.
There we go.
Is that what you're looking
Yep,
for?
that's perfect. And so what Becca's done there is just filled it up completely. We want to make sure there's no air pockets here. Nate, if you could do me a favor and fill this guy also in the Pyrex with that same water.
Same water? All right.
Okay, perfect. And then what we'll do is let's add green food coloring to just one of these. Nate, you can go ahead and add it to yours, just a drop or two.
I always like watching the food coloring.
It
Yeah,
does. It looks
Separate.
really cool.
it's beautiful.
Yeah.
And I'm actually just gonna speed us up a little bit. We'll have an opportunity to sort of see this happen in slow motion for a couple of these. But all right, we've got some green water and some clear water. Nate, can you just top that guy off for us?
Oh, top it off with water?
Yep. So what we're going to do here is something that you can do at home, as long as you have 2 vessels that have the same size mouth opening. I'd recommend doing this with glass jars or glass cups, but it works pretty well with these beakers, so we're going to try it with that. Okay, so what you need is beakers or glasses filled completely up with water like this. And then what I have here is just a little piece of cardboard or cardstock, right? Anything semi-stiff like this that I can put over the top is going to work. What we're going to try to do, Nate, and I'm going to have Nate do this first when you're ready.
All right.
I'm going to have you flip the green one upside down.
Oh, easy.
And place it gently on top of the clear one there. Okay? And we'll
All
keep it
right.
inside the Pyrex pan just in case there is any spillage, Nate.
magician.
You know, life goes on. So what you want to do is, and I won't do it, but I'll just sort of show you. What we're going to do is we're actually going to push this down. Oops. We're going to push this down right on top of the green beaker here, sort of pushing some of the water out of the way. Then you'll hold that down as you flip it up, put it together, and then slide the cardboard.
Gotcha.
Does that make sense?
Yeah.
All right, Nate, I believe in you. I know.
Pressure.
This is
I know.
Okay.
The stakes are high. Beautiful.
Oh,
Okay, great. No, fantastic. And you want me to help with the cardboard?
yeah.
Okay. All right, and then that should just sit right there. And hopefully you can see at home. What do we have? What do we have going on here?
Not too much color transfer, a little bit.
Just, yeah.
Yeah, would you describe that as like a slow color transfer?
Definitely slow.
So when we have
Now-
go ahead.
Oh, sorry. Is that because I possibly lost some water?
No.
Okay.
Actually, we would expect it to be
Okay.
slow in general because when we have 2 things mixed that are the same density, the mixing and distribution of them is going to be not really dramatic, right? When we have
Right.
things that are of high density and low density that get mixed together, that's when we tend to see more significant results. Now, just as before we move on to hot water and cold water, which is more dense, hot water or cold water? And why? Do you guys know?
I feel like it has something to do with how fast the molecules move. I might be totally wrong on that.
cold water. Yeah, because
is what?
is more dense.
Yep.
Because the molecules are not moving as fast.
Yeah,
Okay.
and it allows them to pack more tightly
Yeah.
together in the same amount of space.
And whenever it's hot, they're kind of moving all over the place and bouncing all over each other and
They kind
expanding.
of just spread out.
Yeah.
Exactly.
Right.
So I wanted to try 2 of these. I was thinking of what we do. I've got a number of other beakers here. I wanted to try one where we'll put the cold water on the bottom and the hot water on top, and then we'll do one where we flip it and put the hot water on the bottom and the cold water on top.
Okay.
Okay?
All right.
So let's actually take this guy, and we may be able to safely transfer him over to the side here. Oh, gosh.
Good luck.
Or not safely if I'm not careful. Dun, 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 dun.
What could go wrong?
What could go wrong? And we'll see how that, we'll see if that transfers any more as we go through here in this experiment. All right, so let's do hot on the bottom and cold on the top, right? So we should see the most dramatic effect there. So cold on the top being more dense, what we should have is the cold should sink and the hot should rise, okay?
Okay.
So what we'll have, and Derek, you want to do this one for me?
Sure.
Take some cold ice water there. Let's have you use this one. Fill that completely up for me. And I'm sorry, let's put it in the Pyrex pan so you can actually let it spill over a little.
Is that ice going to affect it?
You know, might cause a slide. It shouldn't be a big deal.
No, but it's right on top.
Okay.
Do you want to get it out?
Can you get it out, Nate?
think
You can? I got fat fingers.
Nope. We'd have to pour it out.
Becca's got tiny fingers.
We could pour it out really quick.
I believe in you. Or you can try to pour it directly into the...
I almost got it. This is like a game.
This is a fun game.
This is such a good game. Okay, let's try that. Try again. Here.
Try again.
It's good teamwork.
Icy will not.
Okay, so we got that cold water. Nate, go ahead and fill this guy up for me with hot water.
Hot water.
And Becca, in the meantime, why don't you put some yellow in our cold water for me?
Okay.
Oh yeah, that is pretty hot.
Yeah, it is indeed. Okay.
There you go.
All right, and then
I'm gonna put this back here so it's not in the way.
Nate, would you put some green food coloring in the hot water? I had intended to bring blue and yellow food coloring, and I thought I did, but I must have been a little colorblind when I was going through my cabinet before this. So what would have been nice about the blue and the yellow is they would have mixed to green, but we're just gonna have to deal with green and yellow mixing. All right, Nick, can you top that up just a little bit more?
Yeah.
Okay, now we actually want to put the cold on top of the hot. And the reason being, I think we'll see the most intense exchange of colors here, because what will happen is the denser cold water is going to want to sink, and that warmer, less dense water is going to want to rise. So, Beck, I'm going to have you do this one if you feel prepared. So it's the cold one. Don't touch that hot beaker, okay? So it's the cold one. Go ahead and push that on top, and just hold it there and flip it gently.
Oh God.
I know. You got this. I believe in you.
Oh God.
Do you want me to try to pull it out when you're ready?
Yeah.
So let's line it up a little.
And yeah, just make sure you line it up there.
You got it?
I think so.
Ready?
I believe in you. I believe in both of you. Beautiful.
Oh yeah, the green is definitely
And again,
coming up really
unfortunately not the best exchange because of the colors that we have.
Cool, but I don't know if it's gonna stay.
It should. Hopefully it will. I don't know how to.
Yeah.
Balancing it.
And look at that. Within like a few seconds.
Yeah. Wow.
Yeah, you can definitely tell, like
And you
whereas
can
here it's
see-
still clear.
You can see the movement in the water too.
Yeah,
Yeah, you can see
kind of
that.
the swirling, right?
Yeah, it is.
Yeah.
Maybe it is. And I think folks at home, you can probably see those bubbles rising there. And
Temperature.
well, still cold on top and warm on the bottom. But this sort of what this demonstrates is this idea of density, right? And how one thing will sink through another, right? So again, if we had a dense piece of oceanic crust hitting a not so dense piece of continental crust, it's going to be sinking through it. Even though we're talking about rocks here in this case, when we talk about the mantle of the Earth, we're talking about an area where rock is heated so much that it actually flows like a fluid. That's one of the things that allows this to happen. The last one I was gonna try was to see if we could just do it the opposite way here. Oh my gosh. Dun, 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 dun. Okay, so we'll try to do this quickly. What would happen if we put cold on the bottom?
I feel like if the hot air wants, or the hot water wants to rise and the cold
Yep.
water wants to stay on the bottom, then it should actually not do anything.
Yeah, it should keep them totally unmixed. And we can see even our control over there with just room temperature water.
It's mixing a little bit. There
Oh
goes
my
that.
goodness. Well, that was exciting.
Wow, missed me entirely.
Did that miss you entirely?
Yeah, it just
Oh,
got you, I
good.
think.
What got me?
Yeah.
Just my
Like
hand.
our elephant toothpaste.
Actually
thing.
wasn't.
All Becca.
It's not even close. Oh my God, elephant toothpaste. Go back and watch the video of Becca doing elephant toothpaste with
That
us.
was our best
Gosh.
science experiment.
It was pretty fantastic.
That was really fun.
Okay, so I'm gonna try to do this. I'm gonna do this quickly. try to get the thing on top. All right, so let's see if we can. Let's just do, Nate, can we just dye this one guy green?
Yep.
Again. All right, and this is the hot water that Nate just dyed green. So I'm gonna put the hot water over the cold water, and we'll see if we can notice any exchange. Again, even our control here, there was very little diffusion of the green, but
There was some.
But there was some. All right, people, you ready? Mm-hmm. Oh, God.
Don't burn yourself.
That's a little bit too hot.
Do you have a? Yeah, there we go.
Okay. There we go. Oh, geez. Okay. Okay, and I'm actually having a little bit of a hard time with stability here. That's not too bad.
There it goes.
Okay, well, hopefully you saw before I totally destroyed it that the green was really staying above the clear water there. That was a little bit messy. Again, this is a little bit easier with glasses that have the exact same size rim, but I thought the visual effect of these was kind of cool.
And bigger rims too, right? Like, it's really actually hard to line up small rims.
It is kind of tricky to line up small rims. So anyways, hopefully you got the main idea there. We're going to take a break, clean up all this water, and we will see you back in just a few minutes in the Homework Hotline studio.
Sorry, we were just cleaning up
Cleaning up
after
my
our,
mess here.
our science experiment. Okay, well, I think, we want to give you the trivia question one more time, if you're just joining us. Hopefully you did enjoy our science experiment, but let's give that to you one more time. Derek.
All right, well, again, the question is, in the 14th century, before spring was part of its name, what was the season called?
All right, so if you think you have an answer to that question, just give us a call, write up the number on your screen just before the show ends at 5:30. And let's also give you our other contact information, because what we do is we answer homework questions, and if you got them, send them in, and we can help you answer those. So let's give you our other contact information real quickly. You can send in your questions on Facebook or Twitter at EG Homework. You can text your questions to us at 970-680-3771, and email us at homework@emilygriffith.edu. So all the ways you can send in your questions to us.
Lots of options.
All right. Derek, do we have questions waiting for us?
We do. We actually have an English question for Sam here. All right, so what is the difference between affect and effect?
Yeah, definitely. It's a classic English problem, right?
Yeah.
Affect and effect. And I do think that we try to do this thing where we're like, affect, effect, and try to like really make a distinction there. But we just like, that's not how we actually speak. We just say affect, and it sounds the same for both of these words. And there are other words like this, but affect and effect are really tricky because their meaning can be kind of overlapping in a sense. And because of that, we tend to run into problems with them.
Do you think we say affect and effect, we say it the same just because we don't know the difference?
Okay, that could be also that we're just like
Safety.
kind of correcting.
It's a safety. Just
Yeah.
effect?
It is kind of.
It should be effective, that's what I said.
I think that I would say that the effect of affect and effect sounding so similarly is that we do just say them like that. But I think that they also, I just don't think that there's that much of a difference in the way that we genuinely pronounce
True.
them, even when we know
Yeah.
the difference. So if you go online and ask Google this question, a great way to kind of think through this is there's a lot of really awesome images that are created to sort of help English students understand this. So there's a classic one, if we could jump to my screen, that uses an aardvark, and it says the arrow affected the aardvark, and then you can see that the effect of the arrow sticking in the aardvark's butt was eye-popping. And so what you can see here is this difference between effect with an A and effect with an E. So effect with an A has a meaning that's closer to like influence, right? And then effect with an E has a meaning that's close to like results, I would say. Another one that I found recently that I think is great is this one, right? So one person affects with an A another person by pushing them into a lake, right? And then the effect, the result on that person is they are now standing mostly underwater, right? Let me just show one more here. You might be affected with an A by the rain, and the effect with an E of that would be that you would get soaking wet. So again, the distinction here is really between sort of an influence and a result. Another word that's often used is impact. There are English teachers that just suggest you should just use the word impact, because impact can be used as a verb or as a noun, and it can essentially mean either of these effects. The word impact can be used for both, and then you avoid any questions about whether you would get this right or wrong. Now, another way to think about this is effect with an A typically is used as a verb, and effect with an E is typically used as a noun. And that's a really good clue that often helps us make the distinction. And what I'll do here, just to test this out a little bit, is, Nate, do you mind if I pick on you?
Not at all.
All right. So Nate, I'm going to pick on you a little bit. I've got a few questions here.
Okay.
So the question to you is, are we going to use affect with an A or effect with an E? Okay. So in this first sentence, we've got winning the lottery immediately blanked his life.
I'm going to go with an A.
Yeah, effect with an A, and that's exactly right. And how did you know that?
Because it wasn't really a result. It's what's happening. It was
Yeah,
having a result.
Would you say
in
it
his life.
influenced? It had an influence on his
Influenced his
life?
life, that's
So
a good
again,
point.
that's sort of the thing that we want to think about. It had an influence. The other thing is, did you use effect as a verb or as a noun?
As a verb.
As a verb in this case.
Right.
I'm sorry if I was putting you on the spot a little bit. But he did use it as a verb, right? It affected his life. If we could jump to my screen again, unless we're maybe running a little bit short. No, I think we're okay. Winning the lottery had a major effect on his life. In this case, we're saying a really similar thing.
Right.
Right? But we're saying a major effect, so effect is now a noun. And we're also saying that it had a major result on his life. We're talking about the results that this thing had, not the influence, but the results.
So could you also think about, because effect and result are very similar,
Yeah.
or impact and all that, is it generally useful to think, if you're still a little bit lost on it, is to replace the word effect with an E with result?
With
and think
impact.
if it still works.
Well, so
or-
impact is what's recommended, because impact could work for either one of these. Listen, I could say winning the lottery immediately impacted his life.
Right.
Winning the lottery had a major impact on his life.
Oh, what I mean is to tell the difference between
Oh, yeah.
affect and effect.
Absolutely.
To just be like
change out the
result.
word influence if you think it's effect, or result if you think it's if you think it's effect with an A, put in
Right.
influence. If you think it's effect with an E, put it in result.
Because it's much more obvious. It doesn't make sense. It's not clear.
That's exactly
flow
right.
in the sentence. If,
That is exactly right. And I think that's the
Yeah.
best way to do it. Make sure it makes sense from that perspective. Just really briefly, I'll mention I have two other sentences here. This one down here, John never smiles. His affect is totally flat. Sometimes we use effect with an A and we pronounce it affect when we do that. And we're talking about a person's sort of emotional state. In that case, totally different meaning, so there shouldn't be any confusion there. Then you can also use affected as a verb. I came up with this sentence, although he wasn't nominated, Bernie Sanders affected a leftward shift in the Democratic Party. And in that case, you're causing a result to happen. So
Right.
it's still effect with an E, but it's used in a verb form.
That one confuses me.
Yeah, so if you're at all confused, my recommendation
Yeah.
is never use effect with an E as a verb, and just start using impact.
or
Got
you
it.
could try replacing it again if it's confusing, and you could say it resulted.
Yeah,
in a-
resulted in a leftward
There
shift.
we go. Okay, that
versus,
makes sense. I can
well,
do
but if
that.
you said influence the leftward shift, you might say, oh, that could maybe work. It could be tricky. So
I think thinking of the meaning of the sentence, but yeah, it's. Yeah,
But,
I guess
hey,
they would both work.
I am with you, and I think ultimately with these things, the bottom line is always we just want to be understood.
Right.
Just, yeah, as long as we're not taking SATs on that.
Right.
Yes, unless we take the SAT, and then we actually want to know the difference. In
Yeah.
which case, pay attention to what I said.
All right. I think we have time for another math question that we can answer.
All right, so we got a math question that says, what is the value of 8 times 9 plus 18 minus 5 times 2, all in parentheses?
Yeah, these order of operations always seem easy to forget, right?
Yeah? I mean, yeah.
I mean, if you're just learning them, then
For
it's
sure. I
easy
mean,
to mix them
they're
up.
not always easy. They are. So if you cut to my screen, I've got problem on the screen. We're going to, as
Wow.
Nathan mentioned, we're going to use our order of operations, or good old PEMDAS.
Did you just sketch that PEMDAS? It's very nice.
Yeah, that's
I
really
did it
good.
really fast.
Purple
did
elephants
it-
may dance and sing.
Yeah. So please excuse my dear Aunt Sally. What did you say it was?
Purple elephants may
dance.
dance and sing.
I love that so much better. That they may dance and sing.
It's because they're purple.
That's because they're purple, they want to dance. So P stands for parentheses, E stands for exponents, M and D stand for multiplication and division, addition, and A and S stand for addition and subtraction. So what this means is that this is the order that we're going to do this. As you may notice, there are a lot of different things going on here. We've got multiplication, we've got addition, subtraction, multiplication. We've got some things going on here. So we need to figure out which way, oops, I lost my 9, which way we need to do them. And math, our language, we don't necessarily read it from left to right. We read it in the order of operations. PEMDAS is the kind of the way that we read math. So what we're going to do is we're going to start with anything inside of parentheses. Now we have 2 sets of parentheses here. And if you ever have 2 things that you're supposed to do, you always want to go from left to right. So if you're ever thinking, oh God, which one do I do first? I go left to right. Or also parentheses, you could also go inside to outside, because sometimes you might see parentheses set up like this. 2 plus 3 minus 2. I don't know, just making it up. So I have 2 sets of parentheses. You would go from inside to outside. That was beautiful. Okay. So left to right. So we're going to start with this 8 times 9. That gives us 72. And then plus, and I'm going to do this all, that means I'm going to actually just rewrite everything here. Sorry. 18 minus 5 times 2. And then now we're focusing on this parentheses. Now here would be another question is I've got subtraction and I have multiplication. Which one comes first? What do I do first? Well, go back to PEMDAS. PEMDAS tells us multiplication and division are going to come before addition, subtraction. So we're going to focus on this part here. So I'm thinking, I'm actually going to do it this way with just the 5 and the 2. So we're going to do recopy everything else because I didn't touch it. And then I'm going to say 18 minus, and then 5 times 2 is going to give me 10. I'm still working inside of these parentheses until I'm totally done. So this time I don't have a choice, I just have the subtraction. So I'm going to say I have 72 plus, and then at 18 minus 10, it's going to give me 8. Now I have whittled my problem down. I've made it much simpler and simpler and simpler until I just have one operation left. So all I have to do now is add the 72 plus the 8, and I get 80. So if you have multiple operations or multiple things to do when you're simplifying and you don't know what to do first, don't always think left to right. It's our good old PEMDAS that tells us what order to do our work in. So, all right, what next?
I think we need to go to the trivia, get an answer, and then go from there.
Okay, go from there.
Sounds
all right,
good.
Derek, what's the answer to our trivia question?
Well, the question again is, in the 14th century, before spring was part of its name, what was the season called? And the answer is Lent.
Did not know.
Yeah, so before spring was called spring, it was called Lent in the Old English. Starting in the 14th century, that time of year was called springing time, a reference to plants springing from the ground. In the 15th century, that got shortened to springtime, and then further shortened in the 16th century to just spring.
That makes sense.
Was it called Lent? Is that any relation to the
Must
religious?
have a religious connection, right? It must be related to
It has
Like
to.
the beginning.
basically the
Got it,
season
yeah.
starts on Ash Wednesday, right? So
Right.
after Fat Tuesday.
Interesting.
It makes a lot of sense. The
Yeah.
religious. I wonder which came first, though.
Oh,
Catholic
right.
Lent, or spring being called Lent, and then
yeah.
Catholic named it Lent because it happened in the springtime.
Or did they call spring?
Right.
Yeah, interesting.
Right.
Who knows which came
Good
first,
question.
the chicken or the egg? Never know.
So I did find out that the fall and spring equinoxes are the only 2 times during the year when the sun rises due east and sets due west.
Yep. And it's when we have 12 hours a day and 12 hours of night too. That's why it's called the equinox, right? It's the point when we're in between we're in between the solstices. So
Equinoxes.
equinoxes, sure. And in the winter solstice, right, we have the least amount of daylight and the most amount of darkness. And in the summer solstice, it's the opposite, right? We have the most light.
Now, one other thing I read, and maybe you can explain this, I'm not really sure how to visualize this. It says, on the first day of spring, a person at the North Pole would see the sun skimming across the horizon.
First
What
day
does
of
that
spring.
mean? Would they see it actually moving throughout that winter, or sorry, the spring to summer period? It says beginning 6 months of uninterrupted daylight. So I'm wondering if it just means you're going to see the sun the whole time, but it's just kind of moving across.
Yeah, I guess that's right, because so it's like, oh my gosh, so as the Earth is orbiting the sun and reapproaching like the spring position, right? So right on the vernal equinox is going to be the moment when you start to see some of that light. And so I guess on that day you would just, the position of the sun would be right on the horizon. And then as you
Okay.
continued into summer,
For the entire day, so you would see it just moving throughout the entire
you would see
day.
it, right, in the spring you would see it just on the horizon, but then each day after that it would get slightly higher
up
in the
and
sky.
lower, yeah.
It'd be really
Right?
cool to see.
And then it would go back down once you hit the summer solstice. It would start moving back down until you hit the fall equinox, at which point it would disappear. Yeah.
All right.
Interesting.
All right. Well, we got to say goodbye. That was a little bit quick. Sorry. But we'll see you tomorrow, 4:30 to 5:30. Same place, same time. Send in those questions. Love you guys.